Granular materials are conglomerates of macroscopic particles, or grains. The defining property of grain interaction is the dissipation of energy every time a collision takes place. Due to this property, it is possible to observe many kinds of exceptional phenomena lying in between the behaviors of regular solids and liquids. In our work, we focus on agitated granular matter. In this case, the energy dissipated by grain interactions is counteracted by collisions with moving walls. Depending on the method and strength of shaking, as also on the container geometry, a remarkable collection of non-equilibrium inhomogeneous stable states can be observed. Our simulational study considers perfectly spherical hard grains of diameter d. This setup consists of a rectangular tall container which is vibrated in the vertical direction. The container base area is rather small. Its size is only 5 particle diameters. This makes impossible the appearance of any inhomogeneities in the horizontal directions, which is why we say the setup is quasi-one-dimensional. The video now shows the evolution of the particles as the container is shaken. We show a 2D projection of the system in the ZX plane. As you can see, for the high frequencies of excitations we choose, the grains arrange in such a way that there is a solid or fluid layer on top of a gaseous one. This state has been previously named the granular Leidenfrost state, due to its analogy with the liquid over vapor phenomena observed in regular fluids. We have now considerably sped up the video to 1 frame per oscillation cycle. On the right, the evolution of the center of mass of the particles is shown. It can be clearly seen that the granular bed is oscillating in a fairly regular way. Let us now compute the Fourier transform of the evolution of the center of mass. 2 peaks can be clearly distinguished: a very steep one at the frequency of oscillation of the system, and a broad lower peak that corresponds to the frequency of the so-called low-frequency oscillations. Furthermore, we show the Fourier transform for different shaking strengths. Remarkably, as more energy is injected, the low-frequency oscillations become slower. These 3 plots show how the frequency of the low-frequency oscillations vary with the energy injection. The inverse dependence can now be easily appreciated. Our paper also includes a model that clarifies the origin of these oscillations. By approximating the average density profile of the system by 2 constant regions of low and high densities, and considering Cauchy's equation for continuum media, we are able to obtain a relation between the frequency of the oscillations and the ratio of the densities of the bed. The agreement between simulations and the model is overall very good, and improves as the shaking strength increases. In the paper, we begin by relating this work with previous research done in wider geometries, and observe the existence of the presented phenomena in convective states. Moreover, a detailed characterization of the oscillations is presented, as well as a second model that reaches similar results considering thermodynamic arguments. Thank you very much for watching.